Dear students, as we have discussed in the last class, we now consider the condition for stationarity of a VAR model where the variables are non-stationary. We use the concept of eigenvalues instead of the roots in the univariate model. Now, a necessary and sufficient condition for stability or stationarity in a first order VAR is that the eigenvalues of pi1 have modulus less than 1. Necessary and sufficient condition for stability or stationarity in a first order VAR is that the eigenvalues of pi1 must have modulus less than 1. Now we explain what is meant by eigenvalues and how it is related to the root of the polynomial. Now we start with the first order system, then we generalize it into pth order. The first order VAR was written as yt is equal to pi1 yt minus 1 plus epsilon t, or I minus pi1 L yt is equal to epsilon t, or AL yt is epsilon t, where AL is I minus pi1 L, is known as the matrix log polynomial. Now, the eigenvalues of pi1 are the roots of the eigenvalues of pi1, eigenvalues of pi1 are the roots of the kth order characteristics polynomial, kth order characteristic polynomial pi1 minus vi modulus the eigenvalues of pi1 are the roots of the kth order characteristics polynomial modulus pi1 minus vi obtained by solving the characteristics equation. Obtained by solving the characteristic equation modulus pi1 minus vi is equal to 0. That is, the determinant of pi1 minus vi is equal to 0. The reverse characteristic polynomial is modulus I minus rho into pi1, and the roots are obtained by solving I minus rho into pi1 equal to 0. This is the characteristic polynomial. This is the reverse characteristic polynomial. We will explain the difference between these two. That is the roots of the characteristic polynomial obtained from the solution. You will get the values for v, and these values are known as the eigenvalues of the pi1 matrix, and the stability depends on the eigenvalues, that is v, eigenvalues v, or the eigenvalues rho, eigenvalues rho. And by considering the values, we will say whether the process is stable or not. Now, the stability of VAR can be explained either in terms of this characteristics polynomial or in terms of this characteristics polynomial, that is the reverse characteristics polynomial. If we define the stability condition in terms of the characteristics polynomial, that is the first one, the condition for stability is that all the eigenvalues, that is all the roots, have modulus less than 1. If we define the stability condition in terms of reverse characteristics polynomial, the condition for stability is all the eigenvalues have modulus less than 1. Modulus stability is that all the eigenvalues must have modulus greater than 1. Here the values of V less than 1 in absolute value. Here rho greater than 1. Now the confusion arises because in the case of univariate model, condition for stability is explained in terms of reverse characteristics polynomial. Whereas in the case of multivariate VAR, it is specified in terms of the characteristics polynomial. In the softwares, you will see this like this. So when you evaluate the AR roots, you will be very clear about whether you are using the characteristics equation or the reverse characteristic polynomial. Now, let us see a few examples to clarify this. Suppose that pi 1 is given as pi 1 is equal to 5 by 8, 1 by 2, 1 by 4, 5 by 8, pi 1. Now, the determinant of pi 1 minus Vi is equal to determinant of 5 by 8, 1 by 2, 1 by 4, 5 by 8 minus V into I, 1, 0, 0. The solution will give you the polynomial 5 by 8 minus V square minus 1 by 8. This can be factored into 0.978 minus V into 0.271 minus V equated to 0 with the roots. V1 is equal to 0.978, V2 is 0.271. And so setting this V in the first or in the second, you will get to V1 as 0.978. So now as both roots have modulus less than 1 in terms of the characteristics polynomial, the process is stable. VAR is stable given that pi 1 is given this. Remember this, the model is yt is equal to pi 1 yt minus 1 plus epsilon t and I minus pi 1 L is yt is equal to epsilon t. Now, the reverse characteristics polynomial is determinant I minus rho pi 1 is equal to determinant 1, 0, 0, 1 minus rho into 5 by 8, 1 by 2, 1 by 4, 5 by 8 is equal to 1 minus 5 by 8 rho square minus 1 by 8 rho square. This will be factored into 1 minus 0.978 rho into 1 minus 0.271 rho and equate it to 0. You will get rho 1 as equal to 1.022, rho 2 as equal to 3.691. Now as you can see, in terms of the reverse characteristics polynomial, both the roots have modulus greater than 1. So the process is stable. So we can explain the condition for stability either in terms of the characteristics polynomial or in terms of the reverse characteristics polynomial. Now consider another example. Another example. Now pi 1 is equal to 5 by 8, 1 by 2, 1 by 4, 2 by 3. So that determinant pi 1 minus vi is equal to, you will get it as 5 by 8 minus v into 2 by 3 minus v minus 1 by 8 is equal to 7 by 24 minus 31 by 24 v plus v square can be written as 1 minus v into 7 by 24 minus v equated to 0. You will get v1 as equal to 1, v2 as equal to 7 by 24. Now as you can see, one root has modulus less than 1. The other root is equal to 1. So the VAR is not stationary. And the reverse characteristics polynomial 1 by 1, 1 itself. The other case is 24 by 7. 24 by 7 means 3.7. So one root has modulus greater than 1 in terms of the reverse characteristics polynomial. In terms of the characteristics polynomial, it is less than 1. So this is not a stable process. This is not a stable process. So we have to, if the VAR system is such that pi 1 is this, then you cannot model this process in level because you have non-stationary variables that will give you spurious results. So you have to extract this root by first differencing. You have to extract this by first differencing. An alternative is you have to test for cointegration. Extracting the root by first differencing is not an efficient procedure. What is more efficient is reformulate VAR into VECM. Now, suppose that, consider this also. The reverse characteristics polynomial was written as I minus O pi 1. Now you compare this with the AL is equal to I minus pi 1 L. Now the reverse characteristics polynomial is just the determinant of I minus pi 1 L where L takes the place of the artificial variable rho. L takes the place of artificial variable rho. So let me say we have a VAR system. We formulate it as a VAR. Then we have the matrix lag polynomial. We evaluate the roots of this matrix lag polynomial. In terms of the characteristics polynomial, the requirement of stationarity, all the roots lie inside the unit circle, that is the AR roots. In terms of the reverse characteristics polynomial, all the roots lie outside the unit circle. If all are inside the unit circle, you can model VAR in level. Otherwise, you have to first difference it, that is one solution, or you have to reformulate it as a VECM using the reparameterization, which we will see in the subsequent classes. So practice these examples to understand what is characteristic root or what is eigenvalues and related concept which we study in mathematics.